So our second presenter is Francesca Ceccato. She is a researcher at the University of Padua in Italy, where she currently teaches geological and geotechnical engineering and numerical modeling in geomechanics. Her main research topics include numerical modeling in geomechanics with a particular interest in the material point method. And Francesca is also the secretary of the TC103, Numerical Modeling Technical Committee of the ISSMGE. And Francesca, the floor is yours.
Thank you very much. So I will start with this talk with a question. This is a question for you, and I think we are progressing with the topic that we just saw in the previous talk. So all of us know that currently in the teaching of geomechanics, but engineering in general, figures, charts, videos are fundamental. And not all teachers are satisfied with the material they have for their lesson. Marina showed yesterday that more than 52% of the teachers are not satisfied with the educational material they have. And even after searching on the web, they cannot find useful material for their classes. So these findings contradict the popular belief that there is no scarcity of quality educational material at the university level. So we need that. So building on this, a collaborative initiative was launched between TC306, Geo-Engineering Education, and TC103, Numerical Method, to address these gaps. So the objective is to develop peer-review, high-quality and shareable educational material by means of numerical method, material that could be used also in introductory courses. So the working group is still on the early stages of this effort, and we decided to start with a very small task, so preparing small static figures, but we plan to prepare more in the future. And what you will see today is a preliminary result of this project, focusing on a pilot case study. This initiative, however, for everybody brought another question. Can we use numerical method in education without teaching the underlying mathematical details? Think about it, and we'll come back maybe later in the discussion. So a preliminary survey was initially conducted among all the members of TC103 and TC306 to explore the availability of ready-to-use material that could be immediately shared. But many instructors said that they have material, we have Excel, I have figure, but this is not ready to be shared, I need to adapt it. So this sentence, I think that confirmed the private nature of teaching, in the sense that everybody prepare his material for his own and is not ready to be shared with others. And I think we will try to break this. Another point that came up from this survey is that most of the material, especially that one coming from TC103, is prepared for advanced courses, and the people want to keep to use it for advanced courses. So this means that if we prepare material, it would be good to have material useful for both basic and advanced courses. So during this project, I think we set up a good methodology. I mean, it could be improved, but the idea is that first, we need to define the teacher needs. And this was done within TC306. Then these teacher needs are passed, in this case to TC103, but it depends on the needs, to prepare this material to address these needs. And the material is then submitted and reviewed like we do in research, okay? When the material is ready, it will be published online, in this case using the website of ISSMG. So let's see a little bit more in details what we did. So first, TC306 collected the teacher needs. Teacher needs should be precise. This is the one that I specifically addressed for this pilot case study. I will read it. So the topic is stress distribution underneath loaded areas. So so the teacher says, in this case Marina, but many of you probably took part in this project. I want to convince my student and myself that the theory of elasticity performed well. I would like to see how the result would differ if the stress distribution was calculated with something more suitable for soil than the theory of elasticity. And I want to see with my own eyes and show students that difference is indeed small. But I also want to provide example when the differences are not negligible. So this teaching need is well written, but to generalize, I think that the teaching need should always identify the specific topic or concept, stress distribution under a loaded area, explain the current challenge of gap, because also who will address this need is a teacher. So you need to understand this material is used for what, to teach what to the student. So student needs to be convinced that the theory of elasticity can provide reasonably accurate result. And what is the desired learning outcome? So I need something to help my student to visualize and compare stress distribution calculated with elasticity or FEM. Then it is also useful to have some context, so how you believe this material will be used, or example where the concept is important to be applied, and also eventually potential format or approaches. Let's say I want an Excel sheet, I want a colorful figure, or something else. Then the material is prepared, and preparing educational material means two things: preparing the product, that is the figure, the model, the Excel sheet, or whatever it is, and the metadata. Metadata is what guides the use of the material. This is a Word file at the moment, and at this specific stage of the project, it contains information about title, the concept of soil mechanics, the articulation of the main idea, and then additional material that is a detailed explanation and suggestion for its structure, and then of course the license of use, that is CC BY in this case. But I think that this should be improved. In particular, I think that metadata should more clearly address or indicate what is the educational challenge or the gap addressed with that material. What is the learning outcome? So what do you want the student learn with that? And also suggestion for basic and advanced courses. Then the material is peer-reviewed. I think that also in peer-reviewed maybe we should improve a little bit, maybe structure a little bit better what this peer review should do. But, and then the material is published in the website of ISSMG. In particular, we have a section here, peer review educational material. And inside there is already some material from environmental geotechnics, from the TC environmental geotechnics. And then there is a new one, soil mechanics fundamental, that will be published during this product. Okay, let's now move to the results of this pilot case study. These products can be downloaded from the supplementary file of the paper and on this link. Supplementary, so the product in this specific case is contour figures of normalized stresses, an Excel sheet, some contour figures obtained with FEM, some PowerPoint slide that maybe can be ready to use for a lesson, and an FEM, all the FEM models. So the first step is the preparation of contour figures of the analytical solution for the stress under strip load. So what I did is to implement in MATLAB the equation of Boussinesq theory that are valid for an homogeneous elastic half space. And this is the product, so a colorful figure that can maybe in some cases replace black and white figure from the textbook. Maybe some student now could find it more appealing or more clear. There is also a figure for horizontal stress and shear stress, and the result of this figure are also written in Excel, and this Excel can maybe be used to create additional figure for classes or to give assignment to the students. I'll open the Excel file to, so this is the folder that is provided as a supplementary material. Ah, okay, wait, how can I do that? Right, okay. This is the supplementary material. As I said, there is the Word file with the metadata, PowerPoint slide that are similar to those that I will show, and the Excel file. The Excel file contains, so it's the result for the stress increment under strip load. So there is a dimension of the foundation and the load, and then the spreadsheet in yellow contains the increment of vertical effective stress, horizontal or shear, and with the normalized horizontal coordinate or the normalized depth, and the depth in meter automatically adjusts with the size of the foundation. And there are the same things for the, let's say, normalized quantities. You can use it to create other figures and so on. Let me share again. Right. Okay. Then there are the numerical models. I used GeoStudio 2024. It is a proprietary software that is quite expensive, but the good point is that you can manage very well the output in terms of color, labels, etc., better than other softwares from my point of view. The model are shared, so for those of you that are familiar with the model or that are running advanced courses with finite elements, they can use them. And I implemented 6 FEM models. The first one is only used to compare the result with the analytical solution. So the load is 100 kPa and the foundation is 1 meter. The material is linear elastic and there is no gravity to better visualize the stress increment. This is, for example, the geometry and discretization of the model. Now the question is, will you show this slide to your students in an introductory course? I'm showing this to you because I have to prove you that are the teachers that the model is built in a proper way, right? So you can trust what they did. So these are the results in terms of vertical effective stress increment, and you can show it to convince students that these two models give the same result. And this can build some confidence in the analytical solution, but also in finite elements. And this is done for vertical stress, horizontal stress and shear stress, and then with FEM it's very easy to get also whatever you like, mean total stress, deviatoric stress, and so on. But I got the good result because the model, as I showed you at the beginning, is properly done, because the boundaries are far enough, okay? Boundaries are far enough, 22B is quite a lot, okay? But if I wasn't so careful in the boundary condition, as we saw before, I couldn't get a good result with a good comparison with the analytical solution. Because if I put close boundaries, I don't get anymore this shape of the pressure bulbs, okay? But, I mean, this model is not that big, because 5 times the size of the foundation, I think that many engineers could think that is a reasonable size, okay? So, maybe this is also something to show students to, you know, promote critical thinking and show the limitation of the model. So, model 2 2 and model 3 are use some, I think, bit more realistic geometry and size of the foundation. Now there is gravity. The difference between the two is that is the Young modulus. So these are used to show students the displacement, basically. So the importance of the stiffness of the soil. One model has a Young modulus of 30 kPa that could be similar of a medium dense sand, and the other one, model 3, 100 kPa that could be very soft clay. And these are the results. So what you can show to students is that the vertical stress increment at the center line just below the foundation are identical in the two cases, but the displacement are totally different because the stiffness is different. So the learning outcome in this case is that we want to show to students that displacement are larger in soft soil because even if the stress increment is identical. Now be careful that this result to students and also to you might sound like trivial, obvious. So this means that you don't have to show immediately the result, but maybe encourage some thinking before. How much do you think the displacement would be if I reduce the Young modulus 10 times or something like that? But then one can say, okay, but this is linear elasticity, no soil is linear elastic. Okay, then what other model you can use? I'm sure that some student will say, we use more Coulomb, right? Okay, more Coulomb is an advanced model. Okay, elastic perspirative plastic model with more Coulomb failure criterion are often adopted to simulate the behavior of coarse grained soil. So let's use this model 4 with more Coulomb with friction angle 35 degrees. And let's use it to calculate displacement. Now, when we use in practice FEM to calculate displacement, the load is far from the bearing capacity of the foundation, right? Because we are on the serviceability limit state, okay? So, if we do this, we can see that the displacement for calculated with more Coulomb are identical with the one calculated with linear elasticity because the soil does not plastify, does not break, because we are calculating settlement of foundation. So students should learn that it seems more advanced, this model, but for this specific application, it is not. And that you have serviceability limit state and ultimate limit state. Okay, and these are two different aspects to be considered. So you can encourage thinking and learning of the student on this type of aspect. Okay, so more Coulomb, okay, I understand. It was not so good for displacement. Maybe let's move to something more advanced. Let's say modified cam clay. Okay, so I did model 5 and model 6 with modified cam clay. Model 5 is identical to the previous one with the geometry, load, and so on, just changing the constitutive model to the modified cam clay. Well, this model does not converge because it has the load applied on the surface. With this parameter, you have convergence issue. Okay, so in FEM, it won't converge. How will you explain this to your student? Now, this is a question that I did to myself. How can I show to my undergrads that maybe knows a bit about cam clay that this model does not converge? They probably need something more on the background of finite element to understand it. Or maybe you won't show it, right? I won't show the model that does not converge. But in this case, I think that maybe students should find a solution. While the model does not converge, what can we do? So there are several possibilities. One easy one is, well, we never built the foundation just, you know, on the floor. There is always a little bit of excavation, at least, right? So let's try with a bit of excavation. So we prepared another model with this small excavation, so all the construction steps, so generation of in situ stress, small excavation, then load application. Now this model converge, and these are the displacement obtained with the modified cam clay compared with the linear elastic model, the one with the soft clay 1000 kPa for elastic modulus. totally different. So here, I think it's practically useful for the student to understand the effect of plasticity, because the displacement are much more concentrated next to the foundation compared to the theory of elasticity, and this is something that we know it's happening in reality, okay? And has some practical implication. So now you can show, for example, to the student that even though the vertical stress increments are similar, the displacement are totally different. And, but this also tells you that the theory of elasticity of business is still doing a good job to calculate the vertical stress increment, right? So it builds confidence on the analytical methods, okay? Then, so how to use this material in basic courses? I think it can be used to enhance student learning experience. They can probably improve digital literacy, improve fundamental understanding of soil behaviors through better visualization. And it's, I think, very important to promote critical thinking. How to use it in advanced courses? Again, comparison between numerical model and analytical solution, show things that doesn't work, to promote critical thinking, promote discussion with students, show model limitations, because this is, it's important. I mean, the model is not good or bad, it depends on reality. It depends on what are the simplifications that are introduced in the model. Then, of course, in an advanced course, you can prepare assignment based on that, ask to the student to implement the model, to do parametric analysis, to make a little bit more confidence with the, or sensitivity, you know, with the numbers. So preparing this educational material requires a lot of effort. For this specific case study, implementing the MATLAB code is more or less 1.5 hours. Preparing all the FEM model is about 2 hours. 2 hours, I mean, the 6 model will open the program, draw the geometry, make the mesh, assign the parameters, run. All of them, a couple of hours. So really, the numerical part is small amount of hours, but the post-processing, it takes a lot of time, really a lot of time, because it means in MATLAB I have the contour. Oh no, the label are too small. No, the color are not good. Maybe I had the line here and there. With the, I choose GeoStudio because it helped me to prepare nice figures that I believe are good for students. But I also, at the beginning, I tried another software, but I couldn't really make nice figures for students. So preparing good figures out of this result, it takes a lot of time. And then, of course, writing the documentation, it's a lot of time. I didn't mention, but the people that review this material also spend some time to check and give suggestions. In this case, Marina and Michele, which I thank. So they had to spend time to look at this material. So no teacher have all this time available for one single topic. But if we take this effort as an engaged community of geotechnical engineering education, I think it is probably doable, okay? So to conclude, I show you this collaborative initiative to prepare high-quality educational material. This requires significant effort, but if we undertake this as a community, I think we can mitigate the solitude of teaching and improve the quality of, of our teaching. So finally, teaching numerical methods or teaching with numerical methods? I think we can do both, in the sense that numerical method can create effective figures to illustrate soil mechanic concept, but please don't give the impression that numerical methods are superior. Always encourage comparison with analytical solution, as we said earlier, and encourage critical thinking. And can we use numerical method in education without teaching the underlying mathematical details? Maybe, but I'm not 100% sure of that. For sure, never ask students to believe the result. So don't say, oh, this is the result of the FEM model, use it to compare, and they believe it is the correct one. They should at least know a little bit what there is behind, okay, because it's important. But this can also be used to encourage curiosity of the student. So what there's behind? Maybe you don't have to teach them. They can do themselves. So encourage curiosity might also be good. Okay, this is all. Thank you very much.
Thank you, Francesca. Do we have questions and comments in the audience?
For answer. Maybe they have answered to the question.
Thank you, Francesca, for the very interesting presentation. Just a comment to say that the French Committee of Soil Mechanics and Geotechnical Engineering has conducted yet a work which is similar to the one you're presenting concerning editing a guideline for numerical modeling with the same strategy. And this work is being translated to English, so maybe in Spanish. Yes, Olivier can say a few words about it, and we can discuss probably during the break. Could be interesting to share what is done in France with the work that you were doing.
Yes, thanks. Good.
Thank you.
Yes, and we also organized the French committee a national challenge regarding numerical modeling, and a new one is about to be opened. So, Marina, good. Okay.
Thank you. Francesca, my warm congratulations by this sentence and this slide. Don't ask students to believe to the results, but encourage curiosity. It's really very important because the question of the slide, can we use numerical methods in education without teaching the underlying mathematical details is a fundamental question indeed. And I have many doubts about the usefulness of using, of illustrating results from finite element method, for example, in undergraduate courses, when students are not aware about the mathematical basis of the finite element model. Okay, so this is a question that deserves much ponderation and discussion. Okay, just another point about the results that you showed about the incremental stresses, comparing finite element results and analytical methods. It would be obviously the results must coincide. Okay. Since we are performing finite element calculations assuming linear elasticity, okay? What the results may be, probably the comparison may be more useful and pedagogical if, for example, we consider a layered ground, okay? And if we consider the layer ground, certainly the differences arise, and for a layered ground we have as well some analytical solutions. So this is a field very interesting to be explored.
In my mind when I started this project, but then I couldn't make it because I mean it was taking too much time. But I think the comparison is indeed interesting. I think that logically for the student, I think it could be good to see what happened with an homogeneous soil. Then with the stratified soil, let's say 2 layers, because we still have an analytical solution. So a small step forward. But then if you go to a lot of layers, then you don't have analytical solution. So, but it's like a logical process, no? To reach more complex reality where it is useful to use numerical methods at that point, right? And I think that this path is important for the students. Not, as they said earlier, go in a room, these are the software, learn how to use them. I mean, this is unacceptable. For me, it's unacceptable because I teach numerical methods at my university, so I spend, an entire course telling them that they need to critically think to the result, compare with the solution, and so on. But of course, I cannot expect that it's done everywhere in the world, right?
Thank you. Thank you, Francesca. I think the work is very interesting. I would just make a small comment on what you just said. Telling students to critically analyze is not enough. So you need somehow in your teaching to make them compare solutions and develop that critical analysis ability or critical judgment in them. And I'll say it again, maybe we will talk about it later.
Another comment, question? Yeah.
Thank you. Just a comment about the example you showed. Sometimes I prefer concepts rather than doing calculations. In this case, in this example, you're calculating stresses. When you solve the equilibrium differential equation, you get analytical expressions that they do not depend on Young modulus and Poisson's ratio. So you may say to students, well, these expressions are quite general. It doesn't matter if the soil, if you have a soil or a rock, because weight is just weight. Maybe the Poisson's ratio is important, but in general, Young modulus is not, does not appear in these expressions. So maybe this is enough to argue that you don't need to do any numerical calculation. And then you can go on and continue. You don't have to demonstrate to show that the stresses are similar in a numerical model or an equilibrium equation if you use elastic theory, because it is, let's say, obvious. If you use concepts rather
but we were addressing a specific need, where I started.
Yeah, I see your point, but it's just, I think we can use numerical methods for other, let's say, more complex problems, and then use concepts and mathematics or basic ideas to demonstrate, to argue that sometimes you don't need numerical models to show that.
Of course.
It's just a comment.
No, okay. But it was addressing, a specific teacher needs, but okay. Maybe there are others that are different, right?
Okay, thank you very much. It's time to move to the... yes. And thank you, Francesca.